Hi friends, and welcome to the Lost Landscape. Let's build a complete picture of how a modern chat model turns your message into its next word. Almost every chat model today is a decoder-only transformer. Your text goes through a chat template, then a tokenizer that turns it into numbers. Those numbers become vectors, which flow through a stack of identical transformer blocks. A final layer turns the result into a score for every word in the vocabulary, and the model samples the next token. Then it does the whole thing again for the token after that. That's the entire loop. Everything else in this video is just zooming into one of these stages. First, your message rarely reaches the model as raw text. The serving system wraps it in a chat template. Special tokens mark who is speaking, where the user's message starts and ends, and a cue telling the model to continue as the assistant. The model has no built-in idea of user or assistant. It only ever sees this tokenized template, so these special tokens are how it learns the shape of a conversation. Next, the tokenizer converts text into integers. The phrase "the sky is" might become 3 tokens, and each token maps to an ID, just a row number. The algorithm behind this is usually byte-pair encoding. It starts from tiny pieces and repeatedly merges the most frequent neighboring pair. So playing might merge into play plus ing. A common word becomes one token. A rare word splits into several. The vocabulary is learned once, before training, but tokenization itself runs on every prompt. Those token IDs can't be multiplied directly, so each ID selects one row from an embedding table, a big matrix with one vector per vocabulary word. A token ID just means, take that row. Now every token is a vector of, say, 512 numbers. And an embedding isn't a dictionary definition, it's a learned bundle of features: grammar, meaning, capitalization, code syntax, all mixed together. No single dimension has a clean human label. Now the real work. The vectors enter a stack of identical transformer blocks. Here's one modern block. Notice the 2 residual highways running straight through. On the first, we normalize, run self-attention, and add the result back. On the second, we normalize again, run a feed-forward network, and add that back. Attention lets tokens talk to each other. The feed-forward network thinks about each token on its own. Every block has this same shape, but its own learned weights. One key point people miss: the blocks don't pass words or probabilities to each other. They pass hidden vectors, floating point numbers. The shape never changes. 3 tokens in, 3 tokens out, same width, block after block. What changes is the content. With every block, each vector becomes a little more contextual. Less this word in isolation, more this word given everything around it. Let's open up attention, the part everyone finds confusing. The trick is 3 roles every token plays. A query: what am I looking for? A key: what do I contain? And a value: what will I hand over if you pick me? Take the sentence, "The animal didn't cross the street because it was tired." To understand it, its query goes looking for an earlier noun. The key for animal matches strongly, so animal's value gets copied into it. That's attention. Every token asking a question and pulling answers from the tokens that match. Where do query, key, and value come from? Each token's vector is multiplied by 3 learned matrices, WQ, WK, and WV. But there's a modern twist for efficiency. In grouped query attention, we keep many query heads but only a few key and value heads, which several queries share. In our example model, 8 query heads but just 2 key value heads. That single choice is what shrinks the memory cost later. Hold that thought. There's one more step before scoring. Attention by itself has no idea of word order. Swap 2 words and the math barely changes. So we inject position. Modern models use rope, which rotates the query and key vectors by an angle set by their position, leaving value untouched. The beautiful part: the rotation makes attention scores depend on the relative distance between tokens. I've made a whole video just on rope. Here, just remember, it's applied to Q and K inside every attention layer. Now the actual formula: for each head, take every query, dot it with every key. That gives a grid of similarity scores. Divide by the square root of the head dimension to keep the numbers from exploding. Apply the causal mask so no token can peek at the future. Softmax turns each row into attention weights that sum to 1. Finally, multiply by the values, a weighted blend of what each token offered. That blend is the attention output. Let's actually run the numbers. 1 query, 1 and 0. 3 keys. The dot products come out 1, 0, 1. The query lines up with the first and third keys and ignores the second. Scale by root 2, run softmax, and we get weights of about 40, 20, 40%. Now blend the 3 values with those weights. The result is a mix, pulled mostly toward the 2 matching tokens. That's all attention ever does, a weighted average steered by similarity. Why the mask? Because when the model predicts the next word, it must not look at words that come after. So we take the score grid and set every future position to negative infinity before the softmax. After softmax, those become exactly 0 probability. Token 3 can see tokens 1, 2, and 3, but never 4. That single rule is what makes this causal self-attention, and it's why the model can be trained on whole sentences at once without cheating. So what exactly is a head? It's one independent attention calculation running in a smaller subspace. Our model splits its 512 dimensions into 8 heads of 64. Different heads specialize on their own. One might track pronouns, another matching brackets in code, another long-range topic. Nobody assigns these jobs, they emerge. Then all 8 outputs are concatenated back to full width and pass through an output projection, which lets the heads mix what they found. This is where those key value heads pay off. Multi-head attention gives every query head its own key and value. Maximum flexibility, but a large memory cache. Multi-query goes to the other extreme. All queries share a single key value pair. Tiny cache, less diversity. Grouped query sits in between, and it's what most modern models pick. In our example, going from 8 key value heads to 2 cuts, the cache to a quarter, same query heads, a fraction of the memory. A few names you'll hear. Sliding window attention. Each token only looks at a nearby window, cheaper for long context. Sparse attention. Only chosen pairs interact. Cross attention. The queries come from one sequence, the keys and values from another, like text attending to an image. And flash attention. This one's different. It's not a new kind of attention. It's a smarter implementation that computes the exact same result while moving far less data on the GPU. After attention, every block has a feed-forward network, and it solves a completely different problem. Here's the clean mental model. Attention decides where to read from. The feed-forward network decides what to compute with what it read. Attention moves information between tokens. The feed-forward network works on each token alone. The same little network applied to every position, never mixing them. You need both, communication, then computation. What's inside the feed-forward network? It expands each vector wide from 512 up to 2048, applies a nonlinearity, then squeezes it back down. The nonlinearity is essential. Without it, stacking layers would collapse into a single matrix and buy you nothing. Modern models use a gated version called SWI-glue with 3 matrices. A gate that decides which features pass, an up projection, and a down projection. Some models go further and swap this for a mixture of experts, where only a few subnetworks fire per token. Now those highways I mentioned, instead of replacing the vector, each sublayer adds to it. Without a residual, a block outputs f of x. With 1, it outputs x plus f of x. So it only has to learn a correction? Keep what you already know and add something useful. This might be a pronoun, plus it refers to animal becomes. This is a pronoun referring to animal. That additive design is what lets gradients flow through dozens of layers without vanishing. One more stabilizer. Normalization. Across many blocks, values can drift, growing or shrinking until the math gets unstable. Before each sublayer, RMSNorm rescales the vector by its root mean square size, then applies a learned scale. It doesn't erase meaning. It just keeps the numbers in a healthy range so the next matrices behave. Modern models put it before each sublayer. That's the pre-normalization design you saw in the block. Let's count our whole model. Per block, the attention projections come to about 650,000 parameters, and the SWI-GLU feed-forward network dominates at over 3 million. Times 8 blocks, that's about 30 million. Add the embedding table, 32,000 words times 512, another 16 million, and tying the input and output embeddings, the total is roughly 47 million parameters. A real model just scales these same pieces up by 1,000 or more. How much memory is that? It depends on precision, the bytes per number. In full 32-bit, our model is about 187 megabytes. In 16-bit, half that. In 8-bit, a quarter. In 4-bit, an eighth. That's why quantization matters. It's the same weights stored in fewer bits. One nuance, bfloat 16 keeps full range but fewer decimals, which is why training often prefers it. It helps to separate three kinds of memory. Weights, the learned parameters fixed during inference. Activations, the temporary values as a request flows through. Embeddings, scores, block outputs, created and thrown away. And the KV cache, past keys and values, deliberately kept around during generation. Training adds a fourth, gradients and optimizer state, but for serving, those three are the story, and the KV cache is the one that grows with every token. So how does that cache work? During the prompt, every block computes keys and values for every token and stores them. Then the model generates a word, say blue. For the next step, it does not recompute keys and values for the whole prompt. It computes them only for blue, appends them to the cache, and the new query attends over everything stored. Each layer keeps its own cache because each layer has its own key and value weights. Recompute nothing, reuse everything. And here's the payoff from grouped query attention. The cache size scales with the number of key value heads. For our model at a 2,000 token context, grouped query needs about 8 megabytes per sequence. The same model with full multi-head attention, 8 key value heads instead of 2, needs 32. 4 times more. Multiply that across thousands of concurrent users, and you see why nearly every production model uses grouped query. This splits generation into 2 very different phases. Prefill, the whole prompt is known, so all its tokens run through the model together, in parallel, filling the cache in one big pass. Decode, now the model produces 1 token at a time, and each token depends on the one before it, strictly sequential. This is the single most important distinction in how LLMs run. Prefill processes many known tokens at once. Decode discovers new tokens one by one. If decode is 1 token at a time, how is training so fast? Because during training, the correct next words are already known, so the model can practice every position at once. Given the predict sky, given the sky, predict is, all in a single pass, with the causal mask making sure each position only sees its own pass. That's teacher forcing. It's why training parallelizes beautifully, even though live generation can't. Why does that matter for speed? It comes down to one ratio, arithmetic intensity. How much math you do per byte you fetch from memory. When you're doing lots of math per byte, you're compute bound. The GPU's cores are the limit. When you're mostly waiting on memory, you're memory bound. Prefill, reusing each weight across many tokens, is usually compute bound. Decoding 1 token at a time reuses each weight barely once, so it's memory bound. The chip is fast, feeding it is the bottleneck. Let's make that concrete with a 7 billion parameter model. In 16-bit, its weights are about 14 gigabytes. To generate 1 token, the GPU has to read every one of those weights. On a card with 1.5 terabytes per second of bandwidth, just streaming them takes about 9 milliseconds. An absolute ceiling of roughly 100 tokens a second, no matter how fast the math is. The fix is batching. Read the weights once, serve many users, turning a memory-bound job back into a compute-bound one. When a model won't fit on one GPU, you split it. Tensor parallelism cuts each matrix into pieces across GPUs. Parallelism inside a block. Pipeline parallelism gives different GPUs different blocks. A token flows down the line like an assembly line. Data parallelism replicates the whole model to handle more requests at once. Big training runs combine all three. But none of them break the rule. For one token, the layers still run in order. We're near the end of the stack. After the last block, one final normalization, and then the language model head. It takes the last token's vector and multiplies by the vocabulary matrix, producing one raw score, a logit for every single word the model knows. In our case, 32,000 scores. High score means likely next word, low means unlikely. But these are still just scores, not probabilities yet. To turn scores into a choice, softmax converts the logits into probabilities, and temperature controls the mood. Low temperature sharpens the distribution, safe, predictable. High temperature flattens it, more varied, more creative. On top, the sampler might take the single best token or the top few. And note, this final softmax over the vocabulary is a completely different operation from the attention softmax inside every block. Same math, totally different job. Let's watch it all happen once. The sky is wrapped in a chat template, tokenized into 3 IDs, looked up into 3 vectors. They flow through all 8 blocks: attention, feed forward, residual, norm, again and again. A final normalization, the vocabulary projection, and out come the scores. Blue wins. We append it, and now only blue enters the next step, reusing the cache for everything before it. Then the model reaches for the next word, and the loop turns again. So, the whole thing in one frame. A language model is really 3 systems: a tokenizer that turns text into numbers, a transformer stack that turns numbers into meaning, and a head that turns meaning into the next token. Inside every block, attention communicates between tokens, the feed-forward network computes within each one, residuals preserve, norms stabilize, and rope supplies position. And the one idea to keep, Prefill reads many tokens at once. Decode writes them one at a time. That single split explains almost everything about how these models behave. Thanks for watching. If this gave you a clear mental model of how a language model actually works, subscribe to The Lost Landscape for a new deep dive every week, and I'll see you in the next one.